So we are talking about value functions. Okay. People remember value functions? Right. So we defined value functions. We said V pi of S equal to expected value under pi of right. And then we define Q pi okay, good. So now we are going to start unrolling their expectation. So people remember this expression, right? So all of you are clear about it. I don't have to explain what is happening there again, right? So V pi S means starting in state S, following policy pi thereafter, and taking the expectations of the returns that I am getting, right? I am going to start unrolling this, right? So what does it look like? So I am going to say V pi of S equal to yes. What can I write here? Huh? GT plus 1, right? But what would be the value of GT plus 1, the expected value of GT plus 1? V pi of whatever state you land up in, right? So let us go, I am going to say that this is equal to V pi of some S prime, where S prime is the state I am going to land up in. We'll quantify S prime in a minute, right? So people agree with me on this, right? So S prime is the state I go to from S, right? So I can take this summation and write it like this. Everybody on board? Okay. Great. So now I did a sleight of hand here, right? So I took GT and then I wrote it as one term plus the expected value of GT, but that is fine because I am anyway going to take a expectation eventually, right? So this is slight reordering of the expectations, right? Instead of taking the expectation of the full expression, I took the expectation of the inner one alone. But one thing you have to remember is it's only a partial expectation because S prime can change, right? So for me to get the full expectation, I need to condition on S prime also. That is why this expression is still inside the expectation. So if this had been the full expectation, I could have taken it out of the expectation. Since it is still only partially conditioned, so I need to condition it on the full thing, okay? So now I have to write it out so that we will get rid of the expectations, okay? So one way of writing out this expectation is to think of it like a generative process, okay? So remember, what did I say we are going to do? We will start in state S, right? Then select actions according to policy pi, right, and measure the expected return, right? So we are starting in state S and you are selecting actions according to policy pi. So what does that mean? Okay, you are using pi, right? And I am selecting actions according to policy pi. So let us say I pick some action A, right? So now what I am going to do, I am going to get some reward corresponding to that RT plus, the RT plus 1 will be something that corresponds to that reward. So but then before I can find out what RT plus 1 is, I need to specify what the next state is going to be. So I need this. So I have taken action A, okay, then I determine what S prime is, and then I determine what right, but I already determined what S prime is, right, so I can do this. Right, so this is one step I am taking. I pick an action A according to pi, right. Now that is going to cause a transition to some S prime according to this P that we have there, right, and once I know what the S prime is, I can figure out what the expected reward will be as well as V pi S prime, because I know what S prime is. So what is the probability that this will be my return? Is this times the probability I will pick action A. So this whole thing gives me the probability that this will be my expected return. Okay, so now I have to do this over all possible outcomes. So basically a sum over S prime. Okay, is it clear how we got this, right? Huh? This one, right? So I have a S A, right? That's I picked a first, then I pick an S prime according to P. Now I have S A S prime, right? So what I need to do is figure out what this expectation of RT plus 1 would be, right? So that is given in my MDP, right? The expectation of RT plus 1 would be given S A S prime. What is the reward? So that is this expectation. I have written it here. Expectation of R given S A S prime, right? And then the future is gamma V pi S prime. So that S prime has already been fixed, so I can just add the gamma V pi S prime here. So the probability that this will be the outcome, right, is the probability of S prime given S and A times the probability of picking A given S. So all these things put together gives me the probability that this will be the outcome, right. So that is the expected outcome for one choice of A and one choice of S prime. So I will have to sum this over all choices of S prime and all choices of A for me to get the overall expectation. So that is essentially what I have done here, summed over S prime, summed over A. Okay, and this is so it's nice, right? So we written V pi in terms of V pi. Right, so this system of, it's a system of equations, right? You can see there is a system of equations, right? You have one equation for every state. How many variables are there? Number of? As many variables as there are number of states, right? The number of states is not the variable, right? That's also fixed. As many variables as number of states. And what is the variable here? V pi of S is the variable, right? So essentially, so instead of thinking of it as a function now, I can think of it as a collection of variables, right? One for each state, right? And I have n such equations and n such variables, and can I solve it? Depends on what? Huh?
It's linear.
It's linear. Huh? N variables, n equations. So when can you not solve it? Huh? Yeah, so when you get dependent columns and so it becomes redundant, so you have multiple solutions and so on and so forth, right? So it turns out, actually I'll show you in the next class, right? These system of equations have a unique solution. Always. Right? By virtue of the fact that the P that you are using is stochastic. right. So the rows of that P matrix will sum to 1, right. So by virtue of that fact we can actually go back and show that there will be a unique solution for this. I just need to write this slightly different in a different notation for us to see that. So I will do that in the next class, right. So this is pretty much has a unique solution, and this is sometimes known as the Bellman equation for V pi, after Richard Bellman, who is one of the pioneers in the field of stochastic dynamic programming. Okay. Likewise, you can write a Bellman equation for Q pi. Right. So anyone wants to tell me what the Bellman equation for Q pi would be? Rest of the actions. So think of it in a generative process, right? So what is the first thing you do when you're thinking about Q pi SA? So start with S, I pick A, right? I mean it's fixed, so there is no summing over there, right? It's S and A is picked, right? So what do I have to sum over next? Only the S primes, because this pi AS is out of the picture here, right? Because I've already picked A, right? So I don't need to sample from pi A, right? So I already picked A, so I just start by summing over S prime. Right, now SA, S prime are all fixed, right? So I can write expected value of R given SA, S prime plus gamma times. Now the interesting question is what goes there. I could write V pi and it will be perfectly correct, but I will not be writing Q pi in terms of Q pi. Summation over all actions. Huh? This is a Bellman equation for Q pi. Okay. So this should also give you one more ancillary equation there, which is and that is the way Q and V are related. And what about Q pi? Can you write Q pi in terms of V pi? That's exactly what the earlier equation was. The Bellman equation, substitute the last summation with V pi, and that is essentially Q pi in terms of V pi. Right, so I cannot write Q pi SA in terms of V pi S. Okay, it has to be in terms of V pi of the subsequent state. Right, but V pi S I can write in terms of Q pi, oops, sorry.